In this video, we discuss two limit definitions of E. In our studies of compound interest in relatively recent videos, we showed that E was the limit as n goes to infinity of 1 plus 1 over n raised to the n. Now, if we let x equal this 1 over n, we know that as n goes to infinity, 1 divided by a very large number becomes a very small number. So as n goes to infinity, x, which is 1 over n, actually approaches 0. So the limit as n goes to infinity of this expression is equal to the limit as x approaches 0 of this. If x is equal to 1 over n, we've got 1 plus x as the base. And if x is equal to 1 over n, we could solve for n by multiplying both sides by n and then dividing by x. So n is equal to 1 over x as well. So this limit and this limit are the same. We will explore this graphically. We've already explored it numerically in our studies of compound interest, but we'll look at the graph as well. And then we'll also look at the graph of this function and see that as x approaches 0, this function approaches the value of E. But they're just basically two different ways of looking at the same thing. This requires us to look at end behavior of a particular function, and this one has us getting closer and closer to 0 from the left and the right. But either way, we get that value of the natural base E. So this is a line y equals E. E is 2.71828182846 according to Desmos.com. And we talked about that limit definition involving the variable n. So let's make a list. Now this is a list of numbers 1 through 100, 1, 2, 3, 4, all the counting numbers from 1 to 100. And then we're going to define a sequence. A of n, or a sub n is what we would traditionally write, is 1 plus 1 over n raised to the n. Now, if I ask Desmos to graph that, it actually graphs a continuous function. We don't want that right now. We just want the points. So I'm going to have Desmos plot those ordered pairs. When we evaluate a sub n at 1, we have a sub 1. When we evaluate a sub n at 2, we have a sub 2, and so on. This is sort of notation that we can use to do that. We're going to evaluate a at all of these values between 1 and 100 and plot them. So we've got a sequence of values. If we wanted to label them, we could. We won't because it's a big mess if we do. But this is what we've got. And we can see that when we graph that sequence, it gets very, very close to the horizontal line y equals E. So I think it's clear that this sequence approaches E as n goes to infinity. Now, instead of looking at that function of n, which is not differentiable, we could instead define a function of x, where the function of x is equal to the sequence values whenever x happens to be a natural number. So I can define this function g of x equals 1 plus 1 over x raised to the x. G of x looks like that. Actually, let me do this. I want you to be able to see those orange points. And we can see that all of those points a sub n lie on the curve for g of x. And then if we want to, we can evaluate g at various values of x or various values of n. Now remember, these are values that we came up with when we were using this as a formula for compound interest. We said if we deposit $1 at an interest rate of 100%, so that at the end of a year, we would get our original dollar plus another dollar back. We'd have $2 at the end of that first year if we're only compounding interest once per year. We can, that's what this function actually represents. If we continue to increase the number of times we're compounding that interest per year, we see that the value of that function approaches E. So when we compound once per year, we get this value. When n equals 1, the value is 2. So if we initially deposited $1, we'd have $2 at the end of the year. But then if we evaluate at n equals 2, this is 1 plus 1 over 2. So that's going to be 3 halves squared. 3 halves squared is 9/4, which is 2.25. And we can plot that point. And then if we compound 4 times per year, we're going to have 1 plus a fourth, or 1.25 raised to the 4th. And if you simplify that, you get this number. if you compound monthly, you just substitute in n equals 12, you get this number. You compound daily, you get 360, you do that 365 times per year, you get this number. If we compounded interest every minute, we do that 8,760 times per year, and we get this number. Or that's, excuse me, every hour. Every minute is 525,600 minutes. If we did that many, if we compounded interest that many times, we'd have this as our value. And then if we compounded interest every second, we'd be doing that 31,536,000 times. And we get this as our value of our function g. And if we compare that to the decimal approximation of e, we see that the value of g agrees with the value of e given by Desmos. The value of g in this table only goes out to the 7th decimal place, and out to the 7th decimal place when we evaluate that function at n equals 31,000, or excuse me, 31,536,000. We have this as our value. So we can see that we're getting closer and closer to e. Now, if we wanted to, we could find the limit of this expression using logarithms, and I think we've done it before. We've done this many times before. So we could do that, and then we'll see that if we use logarithms as well, we can find the limit of this function as this function approaches 0. So let's actually do this one. Even though we've done it before, let's do it again. And then we will show that another way to approach the same problem of finding the value of e is to look at the limit of this function as x approaches 0, as opposed to the limit of the first function as n approaches infinity. So if we let y equal this limit, and then we take the log of both sides, we have natural log of y equals the limit as n goes to infinity of natural log of 1 plus 1 over n raised to the n. I think we did this relatively recently. Then using our log property, that log of a to the n is n times log of a on their common domain. So this is where a is positive. We can bring that n out front. So we have n times natural log of 1 plus 1 over n. This is an infinity times 0 indeterminate form. And we can rewrite that as a 0 over 0 indeterminate form if we divide by 1 over n. Because dividing by 1 over n is the same as multiplying by n. Now we can't take derivatives of these functions of n because we're thinking of n as a natural number, and if we actually plot that, it's just a list of points. It's not differentiable. But if we switch to a real number x, the limit of a real valued function of x, as x goes to infinity, is the same as the limit as n goes to infinity of this function, just because those points on the sequence actually lie on the curve where this n is replaced with an x. So we can compute that. So we have natural log of y equals the limit as x goes to infinity of natural log of 1 plus 1 over x, all divided by 1 over x. Again, we have a 0 over 0 indeterminate form. And we can apply L'Hopital's rule to that. So this is the limit as x goes to infinity of the derivative of the numerator, which is 1 divided by the inside function by the chain rule, plus the derivative of the inside. And the derivative of 1 plus 1 over x is the same as the derivative of 1 over x. If we take that and we divide by the derivative of 1 over x, we see we've got the same thing here. The derivative of 1 plus 1 over x is the same as the derivative of 1 over x. So these guys reduce as x goes to, oops, this should be x going to infinity. As x goes to infinity, 1 over something very large is something very small. This expression goes to 0, and we get a 1. So natural log of y is 1. So e to the natural log of y is e to the first. So y which was defined to be the limit as n goes to infinity of 1 plus 1 over n to the n, is equal to just e. So now we've proved that using pencil and paper and L'Hopital's rule, but we can also explore that limit numerically. And we increase n from 1 to 2 to 4 to 12, 365 to 8760 to 525,600 to 31,536,000. We see that the value of g, which is 1 plus 1 over n, or 1 plus 1 over x raised to the x, is getting closer and closer to e. If you want to, you can type that in directly. Have 1 plus 1 divided by our n value, all raised to the n value. And we have that. We see we have the same list of numbers. And we can see just graphically that if we graph g and we graph that sequence a sub n, the points on a sub n lie on the graph of g. So the limit as n goes to infinity of a sub n is equal to the limit as x goes to infinity of g of x. So they both approach the same value, and that value that they approach is e. Now, if we make a substitution, if we let x equal 1 divided by n, we can rewrite this expression in terms of x. So if x is equal to 1 over n, we can solve that for n. N times x equals 1. So n is equal to 1 divided by x. And then the limit as n goes to infinity of 1 plus 1 over n raised to the n is equal to the limit as x approaches 0. Because as n goes to infinity, 1 over n goes to 0 of 1 plus x raised to the n, but n is 1 over x. But this is an indeterminate form as well. As x approaches 0, the base is 1, and the denominator is approaching infinity from the right and negative infinity from the left. So we have sort of a 1 to the plus or minus infinity indeterminate form. It's an exponential type indeterminate form. If we want to evaluate that limit, we can let y equal that limit. And then we can take the natural log of both sides. And the log of a limit is the limit of the log. You can pull the logarithm inside. And then just like last time, because we've got the log of a to some power, we can bring that power out front. So this is the limit as x approaches 0 of 1 over x times natural log of 1 plus x. And if you want, you can multiply straight across. You have a natural log of 1 plus x divided by x. So this is a 0 over 0 indeterminate form. If x is equal to 0, we get natural log of 0, or natural log of 1 in the numerator. Natural log of 1 is 0 because e to the 0 is 1. And of course, as x approaches 0, x approaches 0. So the denominator approaches 0, which is sort of obvious, right? So we can use L'Hopital's rule. Now, according to L'Hopital's rule, the limit as x approaches 0 of this quotient is the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. Well, the derivative of the numerator requires the chain rule, right? We've got a function inside that logarithmic function. The derivative of the log of a function is 1 divided by the function times the derivative of the inside. The derivative of 1 plus x is just 1. And then the derivative of the denominator is just the derivative of x, which is 1 as well. So we say to ourselves, as x approaches 0, does this expression approach a finite limit? And it does. This is going to 0, so we just end up with 1 divided by 1, which is 1, times 1, which is 1, divided by 1, which is 1. So we just get 1. And that's natural log of y. So if I want to get y by itself, I exponentiate both sides. Say e to the natural log of y equals e to the first. So y, which was the limit as x approaches 0 of 1 plus x, raised to the 1 over x equals e. Now we're going to explore this graphically and numerically, and we'll see that as x approaches 0, this particular function approaches e. Now again, when x is equal to 0, this function is undefined. So what this tells us is that the graph of, let's say, f of x equals 1 plus x all raised to the 1 over x has a removable discontinuity. So it's just like the graph has a hole in it, basically. At x equals 0. And if I am graphing that point, I'm graphing the point x equals 0 and y equals the limit. So I'll say the graph as a whole at x equals 0, y equals e. Again, when I say it has a hole in it, I just mean we get as close as we want to that location, but that's one point that's actually not on the graph, but we get infinitely close to that location, arbitrarily close to 0e. Okay. So this is our function. And we can see that it's well-defined for x greater than some particular number. It turns out that that number is -1, as we'll see in a bit. But we can compute the limit of this as x approaches 0. And we've already done that by hand. I did an open circle there. There we go. And we can see that that lies on the graph. As x gets close to 0 from the left and the right, the y values approach this number, which is e. One way that we can explore that numerically is to plot some points. We'll just let the x values get closer and closer to x equals 0 from the right and from the left. Now, to do that, I think I want to zoom in a little bit. Instead of looking at this interval of x values from -10 to say 40, let's look at an interval of x values from, let's say, -2 to 1. So this is what we've got. If I evaluate f of x at x equals 1, I get 1 plus 1 raised to the 1 divided by 1. So that's going to be 2 to the first. So we get 2. And then if I evaluate at 0.5, I get 1 plus 0.5, which is 2.5, or excuse me, 1.5, raised to the 1 divided by 1/2, which is 2. So let me type it in. Instead of writing f of x1, let's type 1 plus x1 raised to the 1 divided by x of 1. That way we can see it. That way we've got that formula there for us. It's the same. This is the same as f evaluated at x of 1. So if I plug in 0.5 for x, I've got 1 plus 0.5, which is 1.5, raised to the 1 divided by 1/2, which is 2. So 1.5 squared is giving us that 2.25, and we plot it. And then I substitute in x equals 1/10, and then x equals 100th, and x equals 1,000th, and x equals 1/10,000th, and 1/100,000th, and 1/1,000,000th. And it's really hard to see. You can kind of see that there's a bunch of points there that are sort of all on top of each other as x gets closer and closer to 0. But you can see that those points are getting closer and closer to e. And you can see that numerically as well. If you look at the value of e given by Desmos, it's not exactly the same as this one. There's the difference between f evaluated at 1.000001 and e is actually 0.000001. So we're off by about 1/1,000,000. But otherwise, these are the same. These two function values are the same as each other for the first 5 decimal places after the decimal place, or decimal point, excuse me. So we can see that as x approaches 0 from the right, the y values on the graph approach e. We could also look at a table of values for x approaching 0 from the left. When I usually like to start at an integer, so I started at x equals -1, but turns out the function is undefined at -1. It actually has an asymptote there. And you might think, why does this function have an asymptote at -1? Let's actually type in that function again. It's 1 plus the x value raised to the 1 divided by that x value. You'd say, well, if I substitute in -1, my exponent is 1 divided by -1, which is -1. And then we have the base of 1 plus, or 1 plus a -1. 1 plus -1 is 0. So we end up with this 0 to the -1 power. And whenever we have a negative power, we can rewrite that with a positive power. So it actually ends up being a 1 divided by 0 to the first. And so, of course, you can't divide by 0. So the function is undefined there and therefore has a vertical asymptote, x equals -1. So the function gets very close to x equals -1 like this. But then if we evaluate the function at -0.5, we've got 1 minus 0.5, which is 0.5, so 1/2. 1/2 squared, or is that 1/2 squared? It's going to be 1/2 to the -2. If we substitute in -1/2 here, we'll have a -2 power. A 1/2 to the -2 is the same as 2 squared. So you can flip that fraction and flip that exponent. Actually might be simpler, easier to see if we evaluate it on paper. But if you do that computation for all of these values of x that are approaching x equals 0 from the left, you see that the y values get closer and closer to that 2.71828. And this value, the value of this function at x equals -0.0000001 is the same as the value, the decimal approximation of e out to that 5th decimal place. So that's pretty good. Now, I just want to do that computation on paper so that you guys can see where that 4 comes from. But it's relatively simple to see. So I'm evaluating g at -0.5. And 1 plus -0.5 is just 0.5. And I would prefer to think of it as a fraction. So let's think of that as a 1/2. I've got 1/2, and this is 1 divided by -1/2. When you divide by a fraction, you can just flip it. This is actually 1/2 raised to the -2 power. Now, if I want to, instead of making this a -2, I can make it a +2 if I flip the base, if I flip that. I have 2 divided by 1 squared, and that's going to be the same thing. 2 squared is 4, 1 squared is 1, so 4 divided by 1 is 4. And so that's how we get that value. And if you're saying to yourself, how is that equal to that? Well, it's, I think, relatively simple to see. If you have a divided by b raised to a negative power, that's 1 divided by a divided by b raised to a positive power. And you can apply that exponent to both the numerator and denominator here. And now I've got 1 divided by a fraction. We divide 1 divided by a fraction is the reciprocal. So you can see if you've got a over b raised to the -n, that's the same as b over a raised to the +n. And we've just shown that. Now, if we substitute in -0.1 here, this is going to be g evaluated at -0.1. Actually, let's do that one value as well. Or -0.1 is 1/10 or -1/10. So this is going to be 0.9 or 9/10. Actually prefer to think in terms of those fractions. This is 1 divided by -1/10. So that's going to give me 9/10 raised to the -10th, which is 10 divided by 9 raised to the +10th. And if we actually evaluate that, 10 to the 10 over 9 to the 10th, I'm not sure what that is, but I think the Desmos could tell us, and I bet it's like 2 point something. It's going to be close to E. Looks like I must have made an error somewhere. I have 10 to the 10th divided by 9 to the 9th, which is 25. That's nowhere near this. I'm like, what did I do wrong? I have 9/10. They have 2.867. Let's do 1 minus 0.1. Okay, so that's 9/10. And then 1 divided by negative 0.1. So that's negative 10. So I have 9/10 raised to the negative 10th power. Oh, I think I see what I did wrong. It should be 10 to the 10th divided by 9 to the 10th. I think I just divided by 9 to the 9th. That's why I was off by that extra factor of 9, or the extra factor of 1/9. Do. Okay, so that's right, the right value. Okay, cool. I wrote the right thing down on my paper, but I guess I typed the wrong thing. Now, if we don't plot these points, but instead we just plot that open circle at 0e, we can see that as x approaches 0 from the left and the right, the y values on the graph are approaching e. And this is what the graph looks like. It has that asymptote at x equals -1. So this function is actually very closely related to that other function. We said this is f of x1. Now I claim that that's the same as g evaluated at 1 divided by x1. See, if we evaluate g at 1 divided by x1, we get the same thing. So it's just really a change of variables. We're letting the variable for g be 1 divided by x, and we're letting the variable for f be x, or vice versa, either way. It's up to you. You can write it in terms of x and let x approach 0, or you can write it in terms of 1 over x and let 1 over x go to 0, which means that x goes to infinity. Usually the one where the variable goes to infinity is written in terms of n rather than x. But we see we get the same thing either way. We get e. So those are our 2 limit definitions of e. Take the limit of this guy as x approaches 0. Or we can take the limit of this guy as n goes to infinity. And either way, we get e.